Okay, so in this video I'm actually replacing an older video which was done a little bit more poorly on reflection of waves. We first need to look at this concept of wave fronts. If you look at a side view of, say, water waves, if you were able to cut it away, it would look something like this, with your troughs here and your your peaks here and your troughs in the more dotted kind of positions. So what we can do is take a top view of that, and if we were to see waves travelling in this direction, say towards the beach, we could indicate the wave fronts, the peaks, in this way. Same thing if we throw a stone into a pond, hits in the pond there, and you'll have these wave fronts, which this is much more easy to see and more common, I think. They would be travelling in outwards in all directions. So that's just a way that we can represent those wave fronts. Quite helpful, quite handy. So now we come to this idea of phase change on reflection. Remember, phase is to do with the different positions of the wave. All of these dotted ones and the peaks are all of the same phase, or we could say they're 360 degrees out of phase, and the trough is 180 degrees phase difference. There's a lot of different ways you can talk about that. Exactly out of phase, we might say, rather than just out of phase. So if we consider reflection, we're going to see that there is a phase change during that reflection, and it depends on the conditions of the reflection what that phase change will be. It's either going to be 180 degrees phase change, or 0 degrees, or we might call 360 degrees, which basically is no change. Okay, so when we're talking about no change, I'm going to do a video later with some, which might be earlier if you're watching it before this, with some heavy and light strings. That's what they usually talk about, but it's helpful to consider this situation first, I think, where, say, you've got water waves that are approaching a cliff. Here's your jagged cliff, and people might stand up the top and dive off if they're being daredevils or something. Okay, small waves, hopefully they're doing it safely under good conditions with lifesavers. And if we look at the wave fronts approaching this cliff, this is our top view. Here's our cliff, and our land mass and whatever. And here's our wave fronts, blue, approaching the cliff. Okay, they're meant to be all the same distance apart, but I've drawn that a little bit poorly. It's not about the wavelengths or anything. Wavelength doesn't change, nothing else changes, because the medium doesn't change. So your speed, your frequency, your wavelength are all supposed to be the same, but upon reflection at that boundary, we're going to need to know what this phase change is. In this case, it acts like a string that you're flicking. You sort of send a pulse down, and the end can move, the end can shift up and down. So what's going to happen as that moves up, there's obviously nowhere for it to go, and it has to move down again as the pulse reflects. So that positive amplitude is on the water is represented, if we kind of do a side view. Here's peaks, peaks, peaks. If a peak hits the wall, there's nowhere for all that water to go that's under that peak, so it actually has to maintain that peak upon reflection. So with water waves, there is no phase change. No phase change. Because we are having to deal with this extra water that is a positive substance. If we were talking about a string, it's the free end of the string that can move. It's got a positive amplitude that has to first go down, so you can't just change from a positive to a negative amplitude, if you like, or change 180 degree phase for no reason there. Now, where it gets interesting is if we fix that end. So let's just cruise down, make a new situation, because it's getting messy there. If we fix that end in place, this can be a string, and we send a pulse down the string. That pulse, as it gets here, it's going to hit the end, and because that's fixed, it can't go up and down. So there's no way it can go up and down. But this energy has to go somewhere, the energy that's trying to go up. And what happens, you can try this yourself and see what happens. Grab a skipping rope and give it a flick, and you'll just see that it comes back on the other side. Okay, there is a direct phase change. Phase change to the opposite phase, or 180 degree phase change. Where there was previously a crest, there'll be a trough, that sort of thing. And if you were to flick, this is an interesting little test question they give you sometimes, if you were to flick a second pulse at the same time this pulse is coming back, there'll be a point in the middle where they cancel each other out if they're the same amplitude. Okay, so what have we learned? We can use wavefronts to represent the travelling of waves. It makes it easy rather than trying to match what's going on in a side view or something like that. And we've seen that those wavefronts, representing a peak usually by a solid line, that they will change phase if there is a fixed boundary or a position where the amplitude must remain zero. We would actually call this a node in level 3 physics. And if it can move up and down, then you're going to get no phase change, and it'll travel back on the same side initially. And with water waves, that means that peak will slosh up against the end and then slosh back down again, but it has to stay positive if it's positive, because you've got actual water that's doing it. That's something I've seen a bit confused in some textbooks. I think it's quite helpful to have that perspective. So there's your idea of reflection of waves. Maybe it might be helpful, let's do this just one more down here. If we have our cliff face again, and we have water waves coming in. Oops, I hit my arm when I hit that last one. As it hits, you're going to get the reflected phase. It's exactly the same. Okay, remember, this is a travelling wave, so they're actually going to move as a peak. Where it gets a little bit more tricky, let's just do it this way. I'll bring light into the mix. Hopefully I've dealt with everything well enough so far. We've got a glass block, so here's our glass block. Glass and air out here. Air has a lower refractive index, lower density, air density, higher wave speed. And as light waves, there's sort of a way to represent that, as light waves come in, it's going to hit, and upon transmission, just carries on, no phase change. And again, we'll get to this in a later video, so this is a bit quick. But because we're going, this is essentially the same as a fixed boundary. Hang on, did I get that right? Yes. A fixed boundary here. So you're not going to get a phase change upon, oh hang on, I've got to double check my source, make sure I'm right with that. Okay, yep, got myself clear on there. Because it's like being on the string where it's not fixed, it's open-ended, because you're going to a more dense medium. It's not open-ended. Do I say that the right way? Anyway, here's the string parallel here, fixed in place. Here's your string, your light that's coming along. It's going to have to bounce back in the opposite phase. Okay, I'm not representing that very nicely, but there we go. It's going to bounce back in opposite phase. However, and I know we probably haven't covered total internal reflection, but if you have, at this second boundary, going from glass back into air, we're going to have something different happen, because this is like going from, this is like now the water waves, where transmission's still going to be the same. Let's just show that. Terrible spacing of my waves. But upon reflection, you're going to get a phase change. So the peaks are now going to be where there were troughs upon that. Okay, video's gone long enough. You'll have to reflect on all of that and try and come up with the pictures in your mind. Best thing to do is try and relate all situations back to what we call a light string, or a not as light string, and a heavy or a denser string, and you're flicking pulses along there. Okay, there's a separate video related to that. You can look that up if you like. But relate all situations for transmission and reflection of waves to that, and you won't go wrong.